Okay, so far we examined how we can conceptually understand the inverse dynamics. But for real application for the inverse dynamics, when you're analyzing human motion, mostly you have to actually use it numerical solver like a MATLAB, because you will handle human motion with multiple segments like a two or three even more, and that's pretty tough to solve by hand. Okay, so here I'm going to briefly introduce how you can formulate in the matrix form so that you can simply implement it for your MATLAB coding. Let's take a look how your Newton's law, like for the n segments, like kind of sequential equations, like all the forces applied will generate the acceleration at the center of mass of the rigid body will be formulated. So here, as you can see, I can see the pattern like force 1 minus 2, 2 minus 3, etc. And there are constant gravity formulation, offset, and there is an acceleration. So you can actually formulate your n segments force and motion relationships such as identity matrix 1 minus 1 or 3 by 3 identity minus identity matrix, and gravity term with the multiply by the mass matrix and the acceleration. So if I name it this big matrix as a CMM respectively, I can have those matrix form of Newton's law like a CF minus mg equals mv dot. Or maybe you can just formulate the g in a different manner. I can have CF plus mg equals mv dot. Similarly, moment equations could be also formulated as a matrix form. So I can see the pattern. There are actually four torques components like a torque 1 and torque 2 at each end, and also joint forces applied at each end multiplied by the moment arm cross product will generate the angular acceleration with respect to the center of mass. So here I should multiply by cross product of L center of mass length, and for the joint force at the other end, I could multiply L minus L center of mass cross product. But anyway, this shows some simple pattern, and same for the torques and the acceleration. So I can formulate it as identity matrix 1 minus I minus I for the torques, and a moment of inertia I, don't confuse this one and this one, and the angular acceleration vector. And here I should also formulate the torques generated by the joint forces. But compared to the other matrix component, which is a simple algebraic multiplication for the matrix and the vector, here I should handle for the cross product. Cross product should be converted as algebraic form so that you can easily handle the equations of motion. How we can do that? Okay, so here L component is for the three-dimensional is like a 3 by 1 column vector, and force as well is going to be X component, Y component, and the Z component for the KAIST segment is also 3 by 1 vector. So cross product of the L cross and the F can be by definition formulated by this, and your answer, final answer will be 3 by 1 column vector, right? So can I formulate this one as a algebraic formulation of matrix multiplication, such as something like, let's say A hat 3 by 3 multiplied by the 3 by 1 column vector. If you look at this component, let's see, which is multiplied by this one, this row vector, and this B1 to 3, this column vector, I missed the B1 component here, right? And for the second one, I missed the B2 component. And for the third one, I missed the B3 component. So maybe this A hat composed by 0 in diagonal, and here minus A3 and A2 for the first row components for the A hat matrix. In similar manner, I can fill out what's going to be the components for the A hat 3 by 3 matrix, which is a skew matrix. Then your A cross product B can be formulated as a 3 by 3 matrix multiplication with the column vector B, right? So using these characteristics, I can formulate this cross product as matrix multiplication called L hat. And L hat by definition is defined by LC hat vector 3 by 3, L minus LC hat vector 3 by matrix 3 by 3, which is defined in the previous slide. Okay? So by using this hat matrix transformation, I can have all the moment equation in terms of matrix of algebraic form, like a C multiplied by the torque components, L hat multiplied by the force components, which will generate I alpha. Okay. Okay, so before we go further, let me just take one moment to briefly explore more about this time derivative of velocity and acceleration. When we are handling multiple segments, sometimes you can actually setting the coordinate which is fixed to the space so that it doesn't rotate, absolute coordinate frame. However, it's less intuitive, like by defining the angle with the segment angle, like with respect to the vertical or horizontal, it's not really intuitive. Suppose that your knee angle is more intuitive than your thigh is leaning back with respect to the vertical with the minus 20 degrees, and your shank is leaning forward with respect to the vertical. That's not really intuitive. So when you're handling the joint angle, that comes with the body fixed coordinate, which is relative coordinate frame, which is also rotates with the body, right? So like if I define the joint angle for the thigh with respect to the shank, suppose that this is the torso, shank, and the thigh of the human upright posture. This coordinate is attached to the shank and is rotated with the shank, and this coordinate is attached with the thigh and rotates with the thigh. So when you take the derivative of the velocity vector or the angular velocity vector, you should consider your unit vector that is defined for the x of k, which is ik, how this could be formulated. Actually, we handled this in the very first chapter of like a rotational kinematics. So suppose that your previous segment, which is attaching the reference frame for the KAIST segment, is omega with the omega k minus 1. So this is expressed by omega k minus 1 cross product ik. Actually, here is a j components, right? So for the derivative of the rotating coordinate involves the this omega cross term. Maybe what you have learned in the dynamics chapter for your undergrad, right? So if your velocity and omegas are defined from the rotational coordinate, you should also not only just take the derivative of the velocity, you also have to take the term like omega cross v term and then omega cross omega term. Okay, capital omega here. So your like a velocity is defined in the relative coordinate. Note that your rotational motion should be taken to consider for the derivative. Here, omega is like a previous, the omega for the segment is attached to the rotational coordinate. Here is a previous segment's omega. Now, when you're handling the relative velocity derivative, that's the derivative for the x of center of mass dot, which is this one, and that's simply take a derivative of the theta with respect to the time, and that's I think this is some typo. Sorry about that. And that's the Jacobian, what we already defined earlier, and multiply by the theta dot. Same for the acceleration. When you take the acceleration time derivative of the velocity, you can actually formulate this one as a form of Jacobian theta double dot plus Jacobian dot and theta dot. So combining all this, when you are defining the coordinate body attached so that body fixed so that it rotates with the body segment, your time derivative for the MA term is not only just considering the Jacobian express theta angular velocity and angular acceleration, you should also consider omega cross v term, and same for the angular acceleration. But note that when we are handling the planar motion, all the omegas are k vectors, so these turns out to be 0. Okay, so our Newton's equation can be formulated this way, like your acceleration F equals ma term is gonna be now expressed as a Jacobian and capital omega cross V term. So if you formulate this one by one in segment 1 and 2 in segment n, you can see this one as a kind of pattern like a one identity matrix minus I multiplied by the force vector, and this is mg vector, and this is going to be m multiplied by Jacobian angular acceleration and Jacobian dot and angular velocity. And also this one is a cross product, can be switch it as a omega hat matrix. So it's going to be m omega hat j omega term. So your Newton's equations can be formulated as a CF, C matrix and M matrix and J matrix and omega hat matrix multiplied by the force vector and gravity vector and the angular velocity vector. And same for the moment equation. You have four torque components by torque 1 and 2, and the joint forces multiplied by the moment arm, and those moment arm could be expressed by the head for the algebraic matrix multiplication form. Same for the omega cross term as a omega head term here. So for the first and second and like a sequential segment equation, I can formulate it as something like a capital uh, identity matrix multiplied by the vector and the force vector and the moment of inertia I vector and the angular acceleration and the omega head matrix multiplied angular velocity. So if I note it as a C, L hat, I, and omega hat, I can have this moment equation matrix formulation such as CT plus L hat F I omega dot, I omega capital omega hat, and omega. So this matrix formulation can be used when you're solving torques versus the angular motion. So for example, Newton's law, Newton-Euler equation matrix form will be, I'm going to just rewriting again for what we just have worked on in the previous slides. So CF mg is going to be a Jacobian related term and the rotational coordinated rotation, and same for the torques. Torques by the joint torques and joint forces will generate I alpha and also omega hat when the coordinate is rotating. Now I can eliminate the force from using the first Newton's equations for the second one. So if you plug that into the second equation, you will have everything in terms of theta dot, theta double dot, and the torques. So if you rearrange them in terms of theta double dot, omega dot, which is our angular acceleration with this multiplied by the moment of inertia and the Jacobian term with the mass matrix, and this is actuation, the joint torques, and this is all about the velocity related term, and this is all about the gravity terms, which is pretty much similar for general equations of motion, like robot equations or advanced dynamics. You will have the equations of motion as a form of mass matrix, actuation term, and the velocity term, and the gravity term. So you can just apply the torques to generate the motion in the forward dynamics. Okay, so this matrix formation can be also used for the inverse dynamics. Let's examine how we can formulate it for the least square inverse dynamics method. So recall that our Newton-Euler equation for the force and the torques in terms of angular acceleration can be written as this. Okay, so by actually putting in the force, you can calculate the angular acceleration. Same for the torques. Okay, now what you actually obtain from the measurement is using the force plate and measuring the ground reaction force, right? So this force for general n segment is F1 to up to the Fn, and this one is same, like a torque 1, torque 2 up to the torque n. But what you really have and you want to use is only the first segment of those column vector of force and the torque. So you can actually extract out the very first components of this big matrix form. So how you can do that? Actually, for those n by 1 column vector, I can just extract out the first component, which is a ground reaction force measurement. So I will define C1 vector as 1, 0, 0, 0, excuse me, and multiply by the force vector, so I can extract out the ground reaction force only. In similar manner, I can extract the ground reaction torque as well by multiplying C1 vector to the whole T vector, the T column vector. So I can multiply by this C1 vector to the left and right hand side of the Newton-Euler equations of motion. So since this is a little bit complicated, I can just, let's say, define the terminology like a C1 multiplied by the C inverse matrix as a C1 inverse. Okay. So if I formulate it as a least square methods, like all the angular acceleration related term will be original like a measurement, like from the motion capture system for the angular position will be measured, and you can take the second derivative. And also for the ground reaction force measurement, that could be formulated as a theta form from the equations of motion. So your constant multiplied by the angular acceleration will be placed here, and all the others such as a force measurement and the velocity term and the gravity term on the right hand side. Same for the moment equation. Here you have a angular acceleration coefficients here written as this, okay, and all the other measurements such as ground reaction torques and the velocity and the gravity will be placed on the right hand side. So this is a formulation for least square inverse dynamics method, as we have discussed in the previous session. So this is a total like A matrix, and this is a total like B matrix, so that you could formulate your optimal sort of angular acceleration estimate will be formulated this by A alpha equals B, and those angular acceleration that will minimize this error will be obtained from the pseudo inverse. And or in the MATLAB, simply you can do A backslash B, then you can obtain this sort of optimal angular acceleration measurement. Okay, so we've gone through the how we can formulate this Newton-Euler equation for general n-segment system, so that we can implement it for this numerical solver like a MATLAB. And I hope you can actually write your own code to analyze the inverse dynamics of multiple body segments. Thank you for listening.